Hello, ladies and gentlemen, and today I will be presenting my final year project. I recently graduated from Aerospace Engineering at University of Samsun from Turkey, and I'm Tahir Çebi. My mentor is Ahmet Selim Urna. And my project is about analysis and validation of gas surface interaction models for the VLEO spacecrafts using the ADBSat framework. And first, let's dive into the VLEO. So, why very low Earth orbit? And the very low Earth orbit that creates a lot of opportunities for missions and operations like a higher resolution and a lower latency between the ground station and the satellite, and better signals for the critical missions. Also, this regime is defined within the literature as a Kármán line that you can see where the space begins. The 100 kilometer is the Kármán line, and we are focusing on the 100 between to 400 kilometers. Also, like 450 kilometers are be considered, and there is a lot of challenges in this regime. We are not focused on the classical approach as aerodynamic calculations. In this regime, there is an atomic oxygen, and there are other molecules, as you can see in this graph. And this graph contains nitrogen, the atomic oxygen, and helium and hydrogen, like minimal level. And the challenge is more likely to uncertain parameters in this regime. So there is a solar variation in this regime. When we are flying at and the satellite flies at 7 and 8 kilometers per second, which is a high velocity that creates a considerable forces on the satellite. And the challenging part is the uncertain drag that we need to model the molecules in this regime. So ISS, flying at 400 kilometers, and the drag threshold is like 450 kilometers, which the atomic oxygen levels higher than the other molecules. Today, in my project, I focused on the 200 kilometer because of the validation mission, and this regime are defined with the free molecular flow, and a free molecular flow that requires a special models that we cannot apply with the classical aerodynamical approach. So the problem is, the uncertain drag in very low Earth orbit, and the framework that we use is ADBSat panel method tool, which has been developed from University of Manchester. I implemented some of the codes at MATLAB and to get the realistic data for the validation mission. And our research objectives are focusing on the model sensitivities and the validation of the solar mission data, which has been done at 2022 from University of Manchester. And my research has been focused on 5 models in the literature, which is one of them is Newton, which is a simple model for the empirical models, and the Newton is a classical approach for aerodynamics, and Sentman is more close to realistic results. And this focus on the diffuse reflection between the molecules and satellite surface, like the geometry and the panels. And the CLL, DIRA, and Schaff-Camber models are more detailed models than the Sentman model. They are sub-models of the Sentman, which include the complex formulation and focusing on the thermal effects at the atmosphere, also the materials on the satellite. And yes, let's dive into a little bit the gas surface interaction with the models. And GSI is gas surface interaction is has a three type of reflection, and one of the reflections are, as you can see, this is specular reflection. That think like in the normal physics lesson, it is a mirror-like reflection, and the reflection is it comes with a molecule comes to the panel and it's reflect with the same angle, and the other reflection types are more close to the real world. And the diffuse reflection creates creates a outgassing from the surface of the satellite or panel, and that could be measured with different angles and also depending on the material and more parameters for in the model. The uncertain for this uncertain environment in this regime that needs two key points that I will be talking about the next slide, and the other part is classical reflection. And we know the force of drag formula from the classical approach. There is a three key point for like coefficient drag, reference area, and relative speed of the molecules. And flow regime is the free molecular flow that I talked previously, but I need to deep into the two key points, which is one of them is Cousin number. Cousin number depending on the path of the molecules and also the length of the between molecules and the impact surface. And we define with the Cousin number, it is flow regime characteristic in very low Earth orbit. And the one more key point is the speed ratio that is depending on the molecular speed and the temperature of the surface and satellite. The key insight is the flow is not continuum, and we need to model using some techniques. And there is this is like as we talked about previously. This is the reflection types we modeled. We meshed the structure in a triangular mesh method, which is calculated for triangular per meshes, and after that sum into to obtain the coefficient of drag. And the reflection model is applied for all the panels and all the meshes to get sum of the drag coefficient. And the validation of the SOAR mission is the SOAR mission has a model which is 3U CubeSat with 4 panels that are stable, and that creates me from the literature data for reference drag coefficient data, and that operates like I focused on 200 kilometers. The model sensitivity that we talked about previously in the models, I looked at the four models, which are Sentman, Cook, and Cedalera, and there is a key insight in the sensitivity. The Sentman model creates a systematical bias at like above the 9, and that you can see that Sentman model does not give a result at the 200 km because the speed ratio are higher than 9, and because it has a complex formulation in the mathematical format that contains the error function in the cosine function as a speed ratio is a parameter in the formulation. And our conclusion with the SOAR mission is like we capture like 10% error at 200 kilometer altitude, but this is because of the uncertain parameters like the solar radiation and the geomagnetic activity of the satellite. We are working to get better results with the material applied